And yeah, I had to buy a bag of candy, and whoever was coming in, I live in that apartment, there are lots of people were coming in, so I just were just giving them, and then finally I just left it outside because it was just too much already of that fun. So definitely enjoyed it. So happy Halloween. And now I'm out of candy. Yeah. So anyways, looks like we're going to do some antiderivatives now. So let's try something that looks nasty. Let's try number 27. This was a exercise with parentheses. You see the parentheses there? But besides parentheses, there is also ln. So when I try to substitute, I'm going to replace that ln because, again, the natural logarithm is untakeable for us at this stage because we don't have any formulas that work with it. So the idea is that you don't want to panic when you see this type of expression, but do the substitution because definitely we don't have such a formula that contains antiderivatives of this kind. So my problem with this exercise is that we have ln, so I'm gonna try to replace it with a variable u as usual. So not just parentheses, but entire ln. And then taking its derivative to produce du. I will first of all have 1 over whatever it is here, x squared and plus 1. And I will multiply this by a derivative of what's in the parentheses, the chain rule. And this is going to be 2x. So I attach dx to this. And this will be du. So after this stage, you will notice that everything else here is really going to be du, except for the logarithm. How about that? When you say, is that really possible? Well, for our class, they designed the exercises on purpose of this kind. Of course, if there was, let's say, 2x missing, then it's definitely going to be exercise from the calculus 2 class, because then you would need to learn some special tricks about so-called trigonometric substitution. But here we don't really worry about this. We just notice that everything I try to highlight in blue is going to be called as du. So du will be absorbing everything except for that part that we called as dx, except for ln. So the whole point of process is to be able to get rid of this integral sign. And when I have expression of this kind, then definitely I can do that. Then I can call it as a u to the power of 1 plus 1 is 2 over 2 and plus the constant, right? So once again, I used my new favorite formula. If you have nth power of variable, doesn't matter x or u, whatever you like to call it. So then when you take antiderivative, the power increases by 1, and that same exact power will be in our denominator. So instead of u, I have to return back to my substitution, and whatever it is, I'll just square it. So we get ln of x squared plus 1, and this is also squared. And then I divide this by 2 and add the constant. So the point of story, the scariest looking exercises are actually the nicest ones, because we just need to replace whatever's in the parentheses with a new variable letter, and then the rest will be given you the du thing. So I can do one more of this kind just to see that this is really okay. I can try exercise number 22. That should be a little bit prepared here, because when I'm looking at its numerator, I can see the common factor 3, right? So we're going to have 2u minus 1 inside the parentheses. And then we have du. And then we also have this 4u squared and minus 4u and plus 1. So at this stage, I have to substitute. And when it's Alex, you substitute parentheses. No, the denominator is stronger than parentheses. So I'm going to replace denominator with letter u. So let me write this down. That 4u, it's 30u. So I'll replace it with x. How about that? U squared minus 4 times u and plus 1 I replace with letter x. So then I take derivatives, so it'll be 8. 4 times 2 is 8, multiplied by u minus 4, right? U disappears. And this is equal to dx after I attach du to it. Well, now I need to see how this is related with the rest of the story. And the rest of the story has 2u minus 1 with du. So what I can do is actually produce something similar by taking 4 out. So it'll be exactly 2u minus 1 here with du. And then this is equal to dx. So we're going to divide by 4 on both sides, right? Because I don't need that 4. I have just 2u minus 1. I say, Alex, but you also have a 3. I don't care for that 3. 3 is a constant. It goes outside. Constants never bother us. We just want to take care of variables. And looks like we actually did, right? Because whatever I have in this little red box will be replaced with dx over 4. And that's just what we need. So I'm going to take 3 on the outside, put integral. Now, this numerator thing, I can write as dx over 4. And denominator, I can put as 1 over letter x. 1 over x, that's another formula. Remember the special case when you have the logarithm, right? They actually write logarithm of absolute value of x, to be precise. I didn't tell you that last time on purpose. Didn't want to overload you with this too much. But turns out function logarithm has only positive values in its domain. So if you try to get something negative, it's not going to work. That's why we always want to make sure, if we're not given that x is positive, to make it positive. And the way to make it positive is to take its absolute value. So looks like this 3 over 4 will come out. 4 is also constant, but in denominator. ln of x is here, and plus the constant. When it's Alex, you said its absolute value. Yeah, that's how the formula looks like. So now I go back to my substitution. 2u minus 1, right, is instead of x. So please notice that 2u minus 1 could be or positive or negative, depending on u. Let's say if it's number 0, then it's already -1, and we won't be able to take the ln. So I apply absolute values, and that's the point. So we took antiderivative, and this plus constant. Last time I promised that I will show you an exercise that actually makes a little bit of a sense why we need that constant out, right? So it turns out the exercises that actually ask you to find a constant, they give you just a little bit more information. And it's not just taking the antiderivative, but oh, here it is, 37. So that's a little differential equation here. Let's see, what is that? The equation that has derivative. It's called differential equation. So they say that dy divided by dx, so it's actually y prime, in other words, is the same as a 3 minus 2x to the second power. So what I need is to separate my variable letters, so multiply by dx both sides, because x should be with x and y should be with y. So we get only dy, but dx will go to the right side. So I'm changing its sign. So we get a dy on one side, and then it's equal to whatever we have, 3 minus 2x to the second power and dx. And after I separated these variables, I'm gonna need to solve my equation, and the way to go is integrate both sides, because this way I'm not gonna have that derivative. I wanna find what actual function y is, and that function y will be with respect to my variable letter x. And to actually integrate this, I need to spend a little bit of a time with algebra. Actually not, it's 3 minus x squared. No, square is here, yeah, that wasn't here. So I have to multiply these two parentheses twice with each other, because this is a square, and I need to make sure that we have pieces that we can integrate. That square on the outside is no good. Well, we can multiply, so we get a 9. Then I multiply these two and those two, we get a minus 6, and minus 6 is minus 12x, and then we multiply two negatives, we get a positive 4x squared. So each of those pieces I can integrate one at a time, right? They all go under my old favorite power rule formula here. So let's do this. So function y of x now is going to be 9x, right? Because we just have derivative of x is 1, so that's how I get 9. Minus 12, now x is raised to the power of 1, so I need to add 1, so it'll be x squared over 2 plus, and the last is 4, and we add 1, it's going to be 3 power of x over 3, and plus the constant. You see, so what's with the constant? Well, here's a little extra so-called initial condition. So they say if you plug 0 instead of x and instead of y, you should be able to find constant. So they say that y is 0, okay, I plugged 0. They also say that x is 0, okay, I will plug zeros everywhere here instead of x. So what's gonna remain? They say, well, 9 times 0 is 0 minus, I'm gonna say I cancel these, I got 6. Well, 6 times 0 is still 0, right? And 4/3 times 0 is also 0. So we end up with only a constant here, because all of these are zeros, which is the same as 0. So what's my answer? Well, for this particular case, my function y of x is going to be 9x plus 6x squared and 4 over 3 times x cubed. And this is without constant, because constant happened to be 0. If I had some other condition, then the constant will not be 0, would be some other number. So that gives us idea. Remember that it's not just one function, but a family of functions. And that's why they give this so-called initial condition. So I guess I'm gonna move on and get a little bit more of this story. So I'm gonna be, I guess, moving to the next section and get a little bit more about integrals, because if I say, well, derivative, antiderivative, so what is this all for? Actual use of integrals comes to finding areas. If you have so-called definite integral with little extra attached to it, definite integral, then turns out that we can find the area under the curve by finding definite integral of this function, which is x to the second plus 1 dx that varies from 0 to 1. So we can find the blue area, which is not really area of a rectangle or triangle, but area of some curvy thing. How about that? And I can give you a little example of it. Let's say here's one for the figure 5.6 that we can actually calculate as the area. Notice that here we have 1, 2, 3. So it looks like the bottom of this will be 2, right? And the height of this is coming from equation with, it's a line equation, which is y is equal to 2x plus 1. So the top is some slant line. So what I can do is cut this into 2 pieces and find the area of each piece. I just need to know what happens when x is equal to 1 at the endpoints, and x is equal to 3, what happens with y? So y will be coming from equation, right? 2 times 1 plus 1, which is 3 here. And when x is 3, then so try to put 2 times 1. And this will be 2 times 3 plus 1, which is 7. Right? So I can now see the points here. This be 1 and 3. So this side will be 3. Right? And that one is 7. So that upper one is 7. So I guess gap is 4. So I'm going to need to add areas of 2 figures. The one is a square with a bottom part 2 and the height 3. So 2 times 3 is 6. And the other piece is triangle with a height 4 and base also 2. So to find its area, I could just imagine myself a square with area 2 times 4 for the square, right? Which is 8. But for a triangle, I have exactly a half because there are 2 equal triangles here. So I guess this area will be 8/2 or 4. And then I can add these areas, so my area will be the sum of areas of two figures. One of them was 6, the other is 4, and this is 10. Right? So it's interesting, but now why don't I use the integral of 2x plus 1 dx? So we will find the area under the curve that actually starts at 1 and goes to 3. So we can take the antiderivative, but then do a little bit more and get the area. So antiderivative will be what? 2x squared, right? Because this is power of 1, so I add another one, 2/2. Please notice this is the key formula. We always use it pretty much in all the exercises. And instead of 1, antiderivative will be x, right? Antiderivative of 1, because derivative of x is 1. Now, I don't put plus the constant because we have so-called definite integrals, so I need to find its values at point 3 and 1. What does this mean? It means I need to plug upper one, 3, and then I subtract the lower one. That lower one is 1. 1 squared and plus 1. And let's see what we're going to get. So it turns out there is a special way to take care of this. We plug in the upper limit, and then we subtract the value at lower limit. So 9 plus 3 will be 12, minus 1 plus 1, which is 2. So our area is 10. Just like 6 plus 4 was 10. I don't know why I put 0. I guess I wasn't careful. 10 is exactly the area without doing all of this geometric pieces and adding them together. But turns out the way they produce this area is exactly the same. So they break this area into pieces. That's what they're trying to show here. They get almost 10 because those pieces, there are only like 5 of them. But if you break into more pieces, there'll be a bigger area. And when you take a limit, it's going to be 10. But I don't want to get into this limit story with integrals, because that's going to carry us away to calculus 1, the class that actually proves everything. And our goal here is to take everything for granted, basically, because calculus 1 is 5-unit class, and this one is 4. Plus, we'll also use things from calculus 2. So basically, we're covering like 7 units of material, but within 4-unit time period, and that's like half of time. So we don't use these proofs in our class. But one can say, but Alex, in the book, there are proofs, because these books they produce for 5-unit courses, and usually in the book they have a little bit more. And our class is cut into 4 units, and my goal is to make it understandable rather than to give you some stuff that might, well, give some people not very good grade, right? I want you to feel good about this. So let's just practice to do this upper and lower limit thing. So let me do exercise 11 for practice to start. I think we're going to go over the same old stuff here. So we, first of all, don't pay any attention at all to those limits 0 and 1. So first step is just to take this antiderivative. And then on the next step, I will do the extra thing that is in this new little section. I will plug the numbers in. So antiderivative. Power of 4 turns into 5 divided by 5 plus. Next will be power of 3, so that'd be plus 1, 4, and then divided by 4, right? So straightforward use of that formula. And then x has derivative 1, so this is my expression. And now here comes the new stuff. Those limits. Upper limit is 1, so my first step will be to plug in 1 everywhere. Where I see x, I put 1 in. And then I also want to subtract from it the value of 0 that replaces my variable x. So it'll be 3 times 0 and then plus 0. So looks like what I subtract is actually a 0, right? And that's nice. And what we have here will be a 1/5 plus 3/4 and plus 1. So some people can use a calculator, or some people can do it by hand. I can show you that common denominator is 4 times 5, 20. So we'll multiply and divide by the same thing, each fraction, so we don't change it. So that's 4 and 4 here. And the middle one will have 5 times 5. So this way, we're going to have same denominator, 20. Now, what's on the top? What's in the numerator? Well, we have 4 20s plus 15 of them 20s and plus 20 of 20s. So it's 19 and 20, 39 20s. Or you can write 1 and 19 20s, but the calculator will probably give you 1 and 0.95, something like that. Just the same thing. So I would say the suggestion is, when you come to this point, put this all in the calculator, because otherwise the arithmetic here was nice, and the reason I selected was very nice limits, 0 and 1. 0 is my favorite. When you plug it in, everything turns into 0, so you don't have to calculate. And 1 is next favorite. But if you would select something nasty, like say here in exercise 13, limits are 2 and 5, well, you would be sunk in the arithmetic at this last stage. And I guess the arithmetic part is not really what we care much when we do calculus. So I think for a change, I will actually select one with nasty limits just to illustrate you how to plug them in the calculator. Let me get 29 fractions. That's even worse looking. Look at them. 1/3 to 1/2. How about that? Well, maybe it'd be fine because it's e to the power actually, but still, I just want to illustrate that there is nothing to panic, because you always have your little friend with you. I'm talking about a calculator, right? So you can just put them in a calculator. Let me do this. So our goal here is to get better at dealing with those antiderivatives. And the last step was plugging in those limits, 1/3 and 1/2. How about that? So we deal with e to the power of 1 over x, which is also divided by x squared. So I can rather multiply it by dx over x squared. I think this way will be nicer for me to work with, because there are really two pieces that I have here. 1 over x that I want to replace with a new variable. Since I have 1 over x, I can put letter u, because e to the power of u is my favorite formula. Remember, if I have e to the power of u, then its antiderivative will be exact same thing, e to the power of u and plus the constant. So take a derivative of that. In fact, for convenience, taking derivative, I'd rather call it as x to the power of -1, right? So when I take the derivative of this, it's gonna look like -1 in front, and x will be raised to the power of -1 minus 1, -2, right? Remember formula? We subtract 1 when we take antiderivative. We add 1 when we take, actually, when we take antiderivative, we add 1, but I took derivative, so I subtracted. So this is the same as a negative, and it'd be a power of -2, so I bring x squared down, and 1 is going to stay. And notice that x squared and denominator is something that I really need here. So let me write derivative of 1 over x is what we just found. It's minus, right, in red, -1 over x squared with dx is my du. So we have the minus sign only to worry about. Okay, so I'll divide both sides by -1. In other words, I can say, or multiply by -1. So without a minus, negative will go with du. So I change signs on both sides. And this is going to be replaced. So that's a negative du multiplied by e to the power. So let me get this. So that was my substitution. So my antiderivative will go with a e to the power of u multiplied by negative du. And the negative goes out in front. The minus is just like multiplying by constant -1. So -1 gets in front, and we have antiderivative e to the power of u and plus the constant, but I have limits of integration now. So I guess I'm going to continue with this on the next little page. See, these problems, they get lengthy. And it'd be good if over weekend, because the weekend is coming, right, we could try to redo this couple of problems as usual, same exercises is good enough, because you're actually learning when you're able to reproduce the same answers. So it looks like we took antiderivative, so it'll be minus e, and now I have to go back to my substitutions. Instead of u, it's 1 over x power, and pair of limits. One of them is a third, and the upper is a half. Okay, so the last thing I want to do is replace my x with these limits. So the upper is 1/2, so I put instead of x, so I divide 1 by 1/2. And then I'm going to have to subtract from this. And now again, I have that negative e to the power of 1 over, and now we put a lower limit, 1/3. So upper limit and the lower limit, those are ones that I really care about, 1/3, like that. And this is great because we get a plus here, and that'd be e cubed actually, because when you divide by 1/3, it means you multiply by its reciprocal. And this is minus, and that's e squared. So from e cubed, you subtract e squared. I don't think we even need a calculator here. We can just leave it like that. So it wasn't too bad. I thought these fractions will make me feel very tedious, but no, they happen to be nice. So as promised, I think I'm not gonna get any farther than that, but here's the actual formula that I was using. It is called fundamental theorem of calculus, and that's what we're after in here. It's a formula that says if you find the antiderivative, and antiderivative, they call it capital F. Then you plug upper limit, which is here, B, and then subtract value at lower limit, which is at A. So when you subtract them, you get yourself a nice result. And that's all. So we got this special expression. To justify it is going to be not that simple. We need to have another knowledge from calculus 1 to see why, because this is really surprising result. If you start to think about it, it is really surprising result. But if you'd be interested, yeah, we do this in calculus 1 class, and that's something that is really a little bit time consuming. But anyways, here we just take formulas basically and we plug things in. Same thing we do in statistics class, by the way. If you ever decide to take elementary statistics class, we'll just have also some formulas that we'll be going over, and we'll be actually plugging things in those formulas, and they are justifiable intuitively. But in the calculus, it's not. These proofs, they require lots of information and definitions, so they're not that simple. But at least I tried to give you an idea when we looked at this area under that line, right? So we broke into rectangle, triangle, and we saw that this was working miraculously somehow, but turns out it always works. So section 5.3 is just one page, because the next page I don't really want to get into. So 5.3 is a section that will keep working. I definitely need to get more of it. And then section 5.4 is going to be something that continues to work, and then with analogous procedures. And then last section, I think, will be 5.5 from this chapter. So that'd be another interesting little section. Just trying to see what else we're gonna look at here. And then I think we're gonna be moving in chapter 6 after that. So this is areas under so-called curve. So there are various, again, geometric applications that I'm not gonna get real deeply into, because section 5.5 will bring us back to the substitution that we already looked at, because usually to integrate, it's not that simple, because here we just have powers and they're pretty straightforward, or e to the power, but there'll be some of these interesting things. And then maybe I will try to look at some of these actual applications, because we already have I hope a good feeling about this calculus ideas, because I didn't want to get into applications much, because lots of people probably be lost if I throw you on those. So yeah, 5.6. So let's see how this book is structured. And so I will look at some applications that actually show us why we use this derivative. How can this be utilized in real life? Say, find maximum, minimum. Minimum usually is for cost. Usually people want to have a lowest cost, right? Or maximum is maximum largest profit. So you want to maximize. So that's, I think, most intuitive things, because I don't want to get very deeply into economics or into sciences, but I think those minimum maximums, they very popular in this. Before I move to the last chapter, we need to chapter 6, because in chapter 6 there is more integration. In fact, integration is not as nice as finding derivatives, and that there is a problem. In fact, since we can't integrate, we can find derivative of anything. It's straightforward. But antiderivative is a problem, turns out. We will see this eventually. Yeah, here's chapter 6. It says additional topics and additional topics in integration. And all of these later calculus and analysis, differential equations, these classes appear just to help us find those antiderivatives, because to integrate is very tricky, and that's the point. So I guess we're in a good shape, and little by little we're getting into the last chapter 6, so we have time, so we can look at some of the applications of the integral. And of course, if you look at something and interested in me doing it, just tell me or email it to me, and then we'll do it in class if you'll be interested, of course. Because if you know the calculus part, then you can do and physics and whatever applications in business, economics. They have their own words like marginals, is a marginal cost. Well, marginal means derivative. That's all you need to realize. That's how it's actually defined. So then we'll see a little bit worse looking expression. So in chapter 6, you will see something that is not as nice. So we're going to have to do not just a substitution, but some other procedures to find antiderivatives. So anyways, I don't think I want to give you a quiz on this one. We'll do a little more, and then we'll have a little quiz. So I think you want to get used to this. So I'm going to stop recording, no quiz, and I hope you'll have time over weekend